Welcome to Zero Knowledge, a podcast where we explore the latest in blockchain technology and the decentralized web. The show is hosted by me, Anna.
And me, Frederick. In this episode, we sit down with Jacob Eberhardt from the Zokrates team to talk about the toolkit that they're building for zero-knowledge proofs. Welcome, Jacob, to this episode of Zero Knowledge podcast, where hopefully we can dig into a little bit of Zokrates. And hello, Anna, as well.
Hello.
Hey.
So why don't we dig into your background a little bit immediately? And how did you get into working on this? How did you get into blockchain?
So during my studies, I initially studied business engineering and only had a focus on computer science. But then I got more and more interested in computer science and focused on that as much as possible in my studies. And then as I graduated and said I want to learn even more and focus more in computer science, I started working in a distributed systems research group where I'm also still working. But back at the time, there was only Bitcoin and not much else going on in the blockchain space. So I did what I was interested in back then, and that was distributed database systems, highly replicated, highly available NoSQL systems. And I thought about data types that help scalability and conflict resolution in that context. So then when I felt like this topic was covered and Ethereum slowly came up, I became super interested in Ethereum just because it was like a whole new world opening up, the idea that you could have economic incentives being used as a mechanism in computer system design to enable new types of protocols and to have one global state machine. So I found that super fascinating, and also it fit quite well with my background in distributed databases, I would say, because you can't always say that, but generally blockchains are still distributed databases in a way, just with very high replication factors. And so it fit quite well, and then I went all in on blockchains and Ethereum also in my research, and that's how I ended up studying scalability and privacy problems in blockchains, and that's how I ended up looking deep in blockchains and zero-knowledge proofs as a way to tackle these issues.
So you're still a researcher and PhD student at TU Berlin. Tell us a little bit about some of the work that's come out of that. Tell us a little bit about Zokrates.
Okay, so when I started looking at ways how blockchains could scale and also have better privacy properties, it became apparent that the main problem is the full replication, that every computation is repeated on every single node in a network and that every node stores every data item. And if you look at transactions in blockchains from a very high level perspective, you could say it essentially has two steps, I would say. One is to load and persist state, and the second is to compute state transitions. And based on that abstraction, I started looking at, could you off-chain either of those parts? And as it turned out, off-chaining storage is quite difficult, because as soon as you put data to an external system, you can still ensure integrity, for example, using hash pointers, but it's very hard to guarantee data availability, because then the data may not be available because the outside storage system becomes unavailable. So the storage route, we did some experimentation and research there, is useful in particular use cases, but not as general purpose, I would say. In comparison, computations like computing the state transitions can be off-chained very well, in my opinion. And then blockchains only do what they're very good at doing, I would say, and that's storing data, keeping it highly available. So the system can always make progress. We refer to that as liveness. And then we compute the actual state transition somewhere else, and then need to make sure that it was computed correctly where we send it.
So Zokrates is starting as an off-chain computation project.
Exactly. So that was the main idea. And then coming from that application, essentially, I started looking at different approaches of how you could do that off-chaining in a sensible way. Because if you do it naively, you reintroduce trust to the system. You would expect that the off-chain computation is done by some third-party node, and then when the result is written back to the blockchain, it cannot be used because the third-party node could have lied. So what we need to do is make sure that there is a verify step that's executed on-chain or some other mechanism that ensures correctness. And that's a key property for off-chaining computations, that correctness is always given under the weakest trust assumptions possible.
And this is where sort of zero-knowledge proofs come in.
Exactly. So zero-knowledge proofs, they're an established field of cryptographic research, I would say. And they're not very young, but there's more recent results, for example, zkSNARKS construction, that made it practical, that made the proof sizes small, and that made verification cheap, and that made it possible to consider it for such a blockchain application.
I want to get back into that trust factor a little bit, but we can get back to that later, because as people may or may not know, especially from our Howard episode, zkSNARKS has this bit of trusted setup, so I want to know how you deal with that. But how would you define Zokrates? Just like, what's the elevator pitch?
Can you do an elevator pitch for such a complicated project, actually?
One should always have an elevator pitch.
Okay, I assume I'm not very well prepared then, but I'll try. So Zokrates is essentially a set of tools plus a language which enables developers to more conveniently construct zero-knowledge proofs and verify them on the blockchain. Because the low-level cryptography is there. It's there in theory, and as Howard explained very well, there's also libsnark and there's Bellman, which are low-level libraries that allow you to create these proofs and verify such proofs. But the problem is, if we want to use this in the blockchain context, we need a higher level abstraction, in my opinion, so it actually becomes available to developers and can be used by non-crypto experts. And that was kind of the goal for the project initially, to create another abstraction that wraps the cryptographic details and low-level things in a more convenient way, and then also enables optimizations in the process, for example, so that regular developers, as smart contract developers, for example, will have access to these kinds of tools.
That's very cool. And when I did my little bit of research before this episode, I actually realized that I had misunderstood or sort of partly understood what Zokrates is. I thought it was just the blockchain part, where it's just proof verification on Ethereum. But it's actually much more than that. Can you explain a little bit? You mentioned these pieces, what is the data flow in the system?
Okay, so yeah, it's more than that. And I would say there is probably several key components, and I would just start from the perspective that a developer has, and then we can cover the components. So a developer would first need to specify the computation he wants to prove. That means he wants to show that he executed that computation correctly, and also he wants to be able to use private information in the process. That means use some data that does not become public as the computation is executed, essentially. So he would first start writing high-level Zokrates code, and there is a domain-specific language that is specifically tailored to make it easy to specify computations in a natural way, but also in a way that efficiently translates to the cryptographic low-level primitives, so we can still efficiently construct proofs in the end. That's why we choose a domain-specific language and not just went with some arbitrary high-level language that's already established. And then after a developer writes that code, it goes to the Zokrates compiler, which translates it to a provable abstraction. That means generally, with reference to the episode you did with Howard, to an arithmetic circuit, or a rank 1 constraint system, which is another low-level abstraction, but it's quite close in expressiveness. And then as you have that circuit, there's two things that need to happen. For that specific circuit, as you already mentioned, we need to do the trusted setup. And we do not support any highly involved setup phase that is decentralized or distributed in any way at the moment, but it's pluggable. So secure multi-party computations, if they should be used for that trusted setup as an alternative or lower trust thing, could be plugged in.
When you say this more complicated one, is that like with Zcash's trusted setup? Or like the
yeah,
that's a complicated one. Okay.
So what we offer out of the box is just a local trusted setup. So that means for the circuit you generate it by compiling high-level code. You then receive a proving key and a verification key, and you can use those. But if you actually want to be able to convince a third party of the things you've proven, there should be that third party would either need to trust you, or you should do a better, more complex distributed setup phase. So the trust assumption is weaker.
With your background in, distributed computing and how you got into the blockchain space, did you which end did you start in? Was this always the vision to have this whole tool set, or did you start with we're verifying on Ethereum, or did you start with we're gonna do a high level language to generate proofs?
So initially there was that idea of we could use these verifiable computation schemes that are non-interactive and give short proofs that are cheaply verifiable, just to scale blockchains and to give better privacy properties. And since Ethereum back then was like the main network that was actually ready to use and available, it was the obvious choice to experiment with. So the goal was to do this for Ethereum, and today we still mainly focus Ethereum with our smart contract verification, smart contract generation, which we'll probably go to in a minute. But the idea was rather implementing this idea and building only what is needed. And the goal was never to build a domain-specific language in the first place, but just to realize that idea in some sensible way. And proof verification was not even available in Ethereum. So back then, Christian Reitwiesner, who I often synced with, implemented the precompiled contracts that were required for zkSNARKS verification. And I, in parallel, together with students, developed the first Zokrates version that then enabled to write provable code and actually verified on the Ethereum blockchain. So that's where it all came together. And that's why there's still that tight link with Ethereum.
So I feel like in your description of the components, I feel like we got to the part about trusted setup, but maybe we can continue from there. What else is a developer going to see?
So the compilation gives you that arithmetic circuit, or in other words, a set of constraints. And what you essentially prove when you prove that you executed a program correctly is that you know a satisfying variable assignment for the program, so it fulfills these constraints. And that's why, as a step before you can generate the proof, actually, you first have to execute the program. And in this context, that means finding a variable assignment. So in the end, all the constraints are fulfilled, because what you prove overall is that you know a satisfying variable assignment for the program, but you do not expose all these variables. And that's the zero knowledge aspect of it. And then the verifier checks whether you knew a satisfying variable assignment. And that in the end equals executing the program correctly.
Where does the verifier live in this? Is the verifier on chain? Is the verifier in the smart contract?
In the general idea of zero knowledge proofs, there's no specific answer to this. The verifier can live anywhere and can be anyone. But in Socrates, as it's specifically tailored for blockchain applications, the verifier is a smart contract that lives on the blockchain. And as soon as it receives a proof, it verifies the proof. And in case that verification was successful, it stores the result and also stores in the history, of course, that the verification was successful. So then other parties can actually rely on the outputs of the computation.
You mentioned something that I've never really thought about with zero knowledge proofs, that it's sort of a constraint solving problem.
Yeah.
And I mean, I've written like constraint satisfaction systems before, and it's yeah, I don't know. I never really thought about it that way. It makes sense. It clicked in my mind, how zero knowledge proofs actually kind of work. But yeah, so to recap, the developer story sort of is you write your code in this high level language that you've made. It sort of looks like Python, by the way. Was that the inspiration, or? Yeah.
So the initial inspiration was actually a blog entry Vitalik did, where he, when the discussion came up of how zero knowledge proofs could be incorporated in Ethereum and how they work, he started and just gave a very, very simple example of how to prove a simple arithmetic statement in zero knowledge. And I think, I'm not 100% sure, he even provided a bit of Python code, and that's why the syntax was Python-like. And then we thought about it, and I think it's a nice basis for DSL design, and that's just why we went with it.
So you write your code, you generate, like you send this off to the compiler, and then you generate the prover and verification key in this trusted setup. Then you can generate your proof by running this program. You submit the proof on chain, and it's verified on chain.
Yeah, so there's one thing from a user perspective, that finding a solution for the constraint system and then proving that solution, it's two separate steps. But in the end, it boils down to exactly what you said.
What are the sort of resource requirements to generate a proof? Like, do you need a beefy machine, like a massive server to run it? Or like, it obviously depends on what program you write, but for something semi-normal.
This is very, very hard to say because there's not a single metric you can pinpoint it down to. If you look at the constraint system, what's relevant is the number of variables in your program and the number of constraints. But as you display this constraint system in a matrix form, then the density of the matrix also becomes relevant. So it's very hard just for a given program to say how expensive it's going to be. Generally, I would say memory needs to be big, and you need access to a lot of memory, optimally more than you usually have on your laptop, because if you don't have that, you're using swap, and then proof generation becomes very, very slow. So memory is usually a bottleneck, and that's where very large circuits start to fail then.
Going back to this trusted setup thing, I just wanted to touch on this a little bit because, like you mentioned, you can do a multi-party computation style setup that Zcash did, for instance, but the default in Zokrates is just a local generation. So what is the use case then of just the local one? Is it like in more closed environments where you already have some implicit trust between the sort of dApp maker and the user, or is it in private, consortium blockchains, or what do you imagine?
To be honest, it's not because we make an assumption of what the proper use cases would be, but we rather say people need to find out what their trust assumptions, trust requirements are for their specific circuit, and then incorporate the setup that is sufficient or desirable. I think we could in the future support that programmatically, like provide more tools so people can conveniently do distributed setups. We started experimenting with that and also doing an on-chain multi-party computation prototype. So it could potentially simply be that I want to have a smart contract that uses zkSNARKS, and then I say, okay, now I want to do a setup for this contract, and then you have an on-chain coordinator that coordinates that setup and gets contributions from all the parties that want to be involved. But the problem is that you cannot rely on the pure number of participants in that setup, because it's Sybil attacks can easily happen. So the same physical entity participates several times. So in the end, it boils down to, if I do not want to trust at all, I need to participate in the setup. And that can be realized in several ways and depends a lot on the specific use case.
So you mentioned just before that it compiles into a circuit, but what circuit is that exactly? What is this based on?
The circuit is actually in a format, it's called rank 1 constraint systems, and it's not strictly a circuit, but it's equally expressive. And it's just a way to express a set of constraints so that you can then use the zero knowledge variants that are provided by a lower level library, such as libsnark, for example, to generate your proofs.
So does libsnark have like native support to take these rank 1 systems?
Yeah, libsnark enables you to use a translation from rank 1 constraint system to quadratic arithmetic programs. And these quadratic arithmetic programs are then the abstraction the proofs are actually performed with. But it's a common abstraction, I would say, and interoperability discussions for circuit also often, include or propose R1CS as one option, for example, for circuit specifications. So it's a standard format in a way, but the problem with rank 1 constraint systems is that you use what I call witness derivability. So what you have in the high-level language is you have an imperative way of writing your code, and with that, it becomes clear how you derive one variable's value from another variable. If you translate that into a rank 1 constraint system, it's only constraints. It's essentially assertions. And in that process, the information of how one variable can be generated or computed from other variables gets lost. So I would say the rank 1 constraint system is a sufficient abstraction to then build proofs on, but it's not a good interoperability format, because when you get that system, it's extremely difficult. It's an NP-hard problem to find a satisfying variable assignment. And that's why I think we need a better interoperability format, because we have that information in our high-level language.
This is something we've talked about before on the podcast of standardizing. Howard has mentioned several times there is no standard way to write these circuits, so there's no interoperability between libraries and stuff. That's an interesting. I didn't know that this rank 1 constraint system was like even a part of the question here. So I think that's an interesting aspect pros and cons of having that be the interoperability as well.
So just recently, we sat down with Benedikt Bunz from who's the co-author of Bulletproofs, and I've been a little curious about where Bulletproofs could fit in with Zokrates, or if it would ever fit in with Zokrates.
So Bulletproofs are a very intriguing proposal, I would say, because they have the very cool property that they do not require trusted setup, and that's always limiting potential use cases, causing overhead cost for setup procedures, and also, it requires trust, which is usually a very bad thing in the context of blockchains. So that's why Bulletproofs are very cool. They were initially designed for range proofs, but they can also be used to prove statements that are expressed as arithmetic circuits. So it's essentially the same abstraction that zkSNARKS that we use are also based on. So theoretically, we could simply use the same compiler, do the same compilation steps, and just use a bulletproof implementation in the backend instead of libsnark to then be able to generate bulletproofs. The problem here, I would say, is that the verification step in bulletproofs has linear complexity with circuit gates, and that's why the on-chain verification very quickly becomes impractical. And that's why it's viable and quite cool for small circuits, but as your circuits become big, it becomes super expensive to verify. Also, zkSNARKs, they are extremely efficient. They have a proof size of, with a Croth 16 construction and a standard curve, 127 bytes. So it's very, very small. Bulletproofs, they're still quite good, especially like compared to zkSNARKs or other constructions that do not require trusted setup, but they have a few kilobytes in size. So I think we are compatible with bulletproofs. The question is rather, are bulletproofs the right cryptographic tool to do off-chaining of more complex computations? They certainly are the right tool for range proofs and small circuits, but if you want to do complex stuff, zkSNARKs seem to be unbeatable. Verification is of constant cost, and it does not matter how complex the off-chain computation you want to prove is for the verification. And that's different with SNARKs, with bulletproofs, and that's why zkSNARKs are still very, very attractive and practical, although they have that setup issue.
I want to ask a little bit further on that. So I'm curious, can Zokrates already work with bulletproofs if one wanted to? Like, is it possible? And are there other zero-knowledge proving systems that could also be used with Zokrates?
There are multiple other proposals like Ligero or Hyrax that are different cryptographical constructions. I always have a hard time saying it can be used with because they haven't implemented it. So from a theoretical perspective, it could be used. With zkSNARKs, for example, it's a bit different because they model their computations differently. It's not arithmetic circuits that translate to quadratic arithmetic programs, but to polynomials of higher degrees. So because the underlying cryptography works a bit differently, the translation is not quite that straightforward or comes with some inefficiencies if you were to do it. But bulletproofs, to be honest, should be very straightforward to integrate.
It would be cool to have, like, in some distant future, a toolbox like Zokrates that basically analyzes the size of your program. And if it's something very small, it automatically picks bulletproofs. If it's something medium, it's sort of, oh, hey, you need a trusted setup for this because I'm going to use, libsnark. Or like if it's a massive program or you put in some constraint that it has to have no trusted setup, it picks Starks or whatever.
Yeah, that's a very good idea. We should work on that.
Sounds like you're predicting the future, Frederick. I have another question about like different systems. So you mentioned before, like a little while ago, that you had built it around the EVM and Ethereum because that was coming out around the same time. It was very exciting. Could Zokrates also work with other protocols?
The only part that is specific here, blockchain specific, is the verification smart contract. So the logic that checks that the proof is correct, essentially. And this aspect of Zokrates is quite small. It's just a smart contract template, and we fill in the verification key and add as a smart contract operation the computational steps that are needed to verify proofs. So it could done for any blockchain that supports sufficiently complex operations. And it also would need to support these operations in a way that is efficient enough. And that's why Ethereum uses the precompiles for the underlying operations. So you can actually do the verification of proofs within one block interval and optimally many verifications within one block interval. There is room for improvement. Our current implementation uses the Pinocchio zkSNARK, which has proof sizes slightly under 300 bytes for the curve we use. But we could move to a more efficient SNARK, and we're currently experimenting with that. That reduces it to 127 bytes, as I mentioned earlier. Also, the precompiles could just become cheaper because client implementations become better. And that is very blockchain specific. So that could be totally different for a different blockchain. So it could be that another blockchain will be able to verify many more proofs within one block, for example. Also, we could, but the problem is that Ethereum does not support it in the current version, move to a better elliptic curve that allows other cryptographic primitives to be used and is overall more efficient.
And this is the argument behind WASM blockchains, right? And like eWASM and all this stuff is that you can write all these curves, deploy them by yourself. It doesn't have to be a built-in contract or a precompiler.
Yeah, exactly. If we had a WASM VM and this was efficient, then it would be much easier to experiment with new cryptographic primitives. It would not require a hard fork, and everybody could just choose the curve he's most comfortable with, because there's oftentimes also a trade-off between what's the perceived security of a curve and how long has it been around and not shown to be vulnerable, and efficiency of the operations.
So before we move into our next little section that we want to talk about, which is how do you learn all this stuff, I wanted to just slightly personal question. More or less all of Zokrates is written in Rust. Why did you pick Rust?
Oh, that's a good question. Like, we had to do it in some language, and when you're researching, you always try to maximize what you learn on the way. So we thought we may use that very cool new language that has zero cost abstractions, very good type system, and just find out whether it works for us, and it has shown to work very well for us. So I'm quite happy with the choice. It's quite cool. And the good thing is, if we at some point move to WASM, then we can compile from Rust to WASM very easily. So it will also help us make required changes to be future-proof more easily.
So our listeners don't know this, but Frederick is smiling a lot right now as you describe that. So obviously this is not a super simple project, and I think this interview we've gone pretty deep into it. Are there places that people can already find some of this material? Do you have talks? Do you have slides? Like, where would you direct people if they want to see this in a little bit of a bigger picture?
So there's multiple resources. There is our GitHub repository that includes some examples and a very brief setup guide, but I think we could do a better job there onboarding people, but that's something we're actively working on. There are multiple talks that are available on YouTube, I think. So I presented Zokrates initially at the Ethereum DevCon 3 in Cancun. So that talk's available. There's also a talk from the Ethereum Community Conference in Paris. And there's also, I think, a presentation from a meetup in Berlin, which was done together with TrueBit.
Oh, nice.
So I think there should be some videos out there that explain that stuff in another way, and that also have some slides and pictures. Also on my GitHub account in notes, you can find these presentations. So if people would like to check out something more visual, that's where to find it.
Cool. I think we're also going to put at least a link to that in our show notes, but probably some of these other ones as well.
Oh, most importantly, though, there's a research paper on Zokrates, which was just recently presented at the IEEE Blockchain Conference in Canada and actually won Best Paper Award. So I suggest you check that out.
Congratulations.
Thanks.
So I just wanted to ask as well, because in a more general sense, you're still involved with the university and maybe you're dealing with students and people trying to get into this space. What would your recommendations be for if I'm I know computer science or I know programming. I want to know zero knowledge proofs. Where do I start, and how do I actually get up to speed on this stuff?
So I think what you first need to do is to answer the question for yourself, whether you can live with not understanding how it works mathematically in depth. And if you can, then it's much simpler. If you can't, like I did, you have to dig into the papers and read up on that stuff and probably learn a bit more about cryptography and proof systems in the process. So I think the Pinocchio paper is a good point to start because it's quite accessible and already describes a mapping from arithmetic circuits to proofs. And then generally the work of Eli Ben Sasson is very, very cool. And I recommend you check that out if you're really interested in theory. Another approach would be to just start playing around with libsnark or Bellman, which are the libraries that allow you to compose provable arithmetic circuits on a very low level, although it's not super usable in my opinion, or at least requires quite some expertise because it's not straightforward of how you would express a computation in an arithmetic circuit in the first place. But that would also be an option. And then the third option is looking at domain-specific languages like Socrates and trying to understand how they work internally, gaining insights on that translation process. Because I think if you understand how you go from a high-level program to a provable abstraction and then just look at that proof system as a black box and just study its properties a bit, it can get you quite far and you can meaningfully contribute to the further development without having a very strong mathematical background.
So you were telling me that you actually are working on, or maybe have submitted a paper about the different approaches to off-chain computation. Can you maybe just briefly give a little teaser about what you have there?
Yeah, okay. So very briefly, from a high-level perspective, we tried to put together a paper that describes the different approaches to off-chain and computations in general. So not only the verifiable computation schemes we talked about now as one options, but also other promising approaches that are currently researched, and also not so promising approaches, maybe just to get an overview of what's out there, what the possibilities are, and what the trade-offs is. So maybe we just mention a few other high-level ideas or categories that that can be used in the context of off-chaining. So one would be enclave-based systems that rely on trusted execution environments implemented in hardware to execute code of the blockchain in an enclave, for example, in an Intel SGX system. And that can also be privacy preserving because data does not leak and can be sent to that enclave in an encrypted way. And then the result can be published to the blockchain together with an attestation that involves several trust assumptions regarding Intel's SGX attestation service. But it is one option, and it's actively being researched and also built by Enigma, for example, who initially proposed a secure multi-party computation protocol, but then shifted over to trusted execution environments just because it's more practical today. And I don't think it's completely unreasonable to explore that space. And also Ekiden, which is a proposal by Oasis Labs. They also try to use trusted execution environments and published a paper on how to best do that. So that's one approach. Another one I just briefly touched already are secure multi-party computations, where you have the idea that instead of executing some function on chain in a way that the data becomes public that's involved in the computation, you use a network of nodes and distribute the data to these nodes in a way that no node knows more than a meaningless share of the overall data. They then do computation on top of that data. An intriguing property of that system is that if you then, after that computation that was done independently by every single node, if you recombine it in the end, you get the meaningful result, which equals the application of the function to the original secret data. If you then publish that on the blockchain and make sure that correctness is given, and for that you can use a public audit trail that's proposed by some secure multi-party computation protocols, then you can also have a way to do privacy preserving off-chain computations. However, it's not very practical, I have to say, because these multi-party computation protocols, as we have them at the moment, they're not very fast.
What's an example? I mean, is there any projects that we might know that are doing this?
I'm only aware of Enigma, who proposed that initially, but then I think they're still interested in it and doing it, but I'm not sure how active that is.
It also sounds like a lot of these different solutions or different ways to do off-chain computation are sort of use case dependent. Like you can't do a multi-party computation for like zipping a file because you need all of the data to be able to analyze it to create the most optimal compression. Depending on which compression algorithm you use, but whatever. But on the other hand, something like a MapReduce, where you split all the data into pairs and like send 2 pairs to a person, and then they compute this, and then you send the next 2 pairs in a sort of binary tree structure. That's very easy to distribute. I mean, that's sort of like known.
Exactly. And we wondered how these different approaches compare, what their properties are, what the on-chain verification complexity is, what the off-chain computation complexity is, whether they're post-quantum secure, whether they support privacy features, what the security assumptions underlying these systems are. So that's why we try to compose a big picture overview of these approaches. Another approach, for example, would be incentive-based off-chain computations as implemented or proposed by Drubit, for example, where you have an economic security assumption essentially and just assume that people will meaningfully contribute to the network as long as there's no economic incentive to do so. And by incentivizing properly, you can make sure that false results published to the blockchain will always be challenged, and eventually the correct result will be on the blockchain.
So Frederick, you know how you had just earlier said it would be really cool to have this toolbox that would like automatically choose different zero knowledge proving systems? When it comes to off-chain computation, like would there also be, like, do you think that's kind of the future, that there'll be like a meta system that will basically start choosing the ideal one? Or do you think that every protocol will be tied to like one preferred off-chain?
Well, it's the use cases are a lot more dependent on what you're actually trying to compute, and it's a lot larger system in a way. Like it I mean, for some things maybe, but in some cases, your entire application is this way to do the off-chain computation. So might be hard to like properly abstract, because like you can't just write a general program that, you know, from that derive some information on how it should be distributed. To my knowledge, at least, maybe someone comes up with such a structure, but it's a lot more complicated question.
Also, if I may add to this, there's very different security assumptions for all these approaches. And I think different networks, different players, participants feel comfortable with different security assumptions. A cryptographer looks totally differently at things than a person just setting up their private network where they control their hardware. So I think, time will tell what people will accept and what not, but I don't expect there to be one single answer. So I also don't expect that it's necessarily algorithmically decidable which off-chaining pattern would be optimal for a given use case.
So we're talking about this kind of space right in between, you know, industry, these different applications of off-chain computation patterns and like toolboxes that people actually use for applications, but it's also very academic. Obviously, it's a research project, and like you analyze these industry applications as a form of academic research area. How do you feel like the industry and academic spaces compare? Like, what are their motivations? How do they move? And
Oh, that's a good question, because I think in the context of blockchains, they moved closer together than they've ever done before. And I think that's because blockchains they don't have straight up business models, you could say. So the financing models for blockchain related projects changed. And also there's a lot of research involved at every single blockchain project at the moment, just because there are these scalability limitations. There is no perfect solution to privacy at the moment. So every single project tries to link with academia, talk to academia, also do research within their industry project. So I think that's why both spaces moved close together. Also, academics are very happy that their theory finally sees applications that proof systems are actually used in a meaningful way now. And so I think it's quite cool momentum in the space at the moment that makes both spaces move closer together, and also helps academia to make the point that their contributions are more meaningful as it may seem sometimes.
We heard this from Howard as well, that it's not only that it's cool that the theory gets used, but that it gets used so quickly that a paper can be published and a couple of months later there's some proof of concept implementation somewhere by someone.
Yeah, for example, Howard's DISC system, they just published to scale computations that would work super well with Zokrates, because it would just allow proof generation to be sped up a lot. And that's one of the things, or one of the contact points that you just mentioned, where it just fits very well together, and it feels like it was just the missing piece in the puzzle, and then it gets adopted super quickly. Also, there's a big pull from industry, I would say. There is funding of research projects in a way that we've not seen traditionally. There's cooperations between industry and academia in a way that we've not seen before. So, yeah, it's quite cool.
It's interesting, Benedict, we also had that conversation. The one thing he added to this was we were talking a little bit about naming and how these academic concepts are getting named in much cooler ways. And this and Zokrates, I think, falls into that. Bulletproofs, DISC, these are cool compared to what they would have originally been called, which were these long, very technical names of projects. And I think this might be a good kind of ending point for this podcast, but where did the name come from, Zokrates?
Oh yeah, just one thing I may want to add. So these names are cool, but they're a bit difficult for academic papers. So that's why we now need subtitles. Okay. Also, I like that Benedict, especially in the acknowledgement, put the person that came up with the name.
So where did Zokrates come from?
I don't know. I was talking to one of my students back then, and we felt like we need a better name because we had that project, and on GitHub it was called Verifiable Off-Chain Computation something.
Yes.
And we're like, okay. And then Christian Reitwiesner asked me to present at the meetup in 3 or 4 hours. And then we were like, okay, I think we need a name. What would be suitable? And then we came up with the quote by the philosopher Socrates. It goes something like, I know that I know nothing. And then we thought we briefly moved to, I know that I show nothing. And we made that Socrates to hint at the zero knowledge property. And then we felt this is quite... a cringe moment. We can't actually say that this is where it came from. So we just went with Socrates and never told anyone where it...
I love that. That's amazing. I love that you think it's cringeworthy too. That's hilarious. Never to be spoken again. Although it's obvious that Zokrates is Socrates somehow, but that's really cool. This was so much fun to explore Zokrates with you. And yeah, I just wanted to say thanks so much for kind of taking us in to this relatively complicated project that you have. And I really hope that our listeners got something out of this. I think, as we mentioned before, it's probably a good one to, if you're really into this, to go check out a lot of the other resources that are out there, specifically like graphs and sort of images to show those components. I know that we've looked at that, and that's been super helpful. Yeah. So thanks so much for coming.
Yeah, thank you very much for having me. It was an honor to be on your podcast.
And to our listeners, thanks for listening.
Thanks for listening.